position in this vocabulary, the second position is assigned. Is my slide visible to all of you? Is my slide visible? Okay. And I am audible, right? Okay. Okay, so let's start the discussion. Yeah, so today we will be discussing the week 10 of this course. This course title is Deep Learning, and this course was originally taken by Professor Sudarshan Iyengar, Professor and Head of the Department of Computer Science and Engineering, IIT Ropar. Myself, Ayan Paul, I am a PMRF research scholar from IIT Kharagpur, and I am a TA of this course. By TA, my duties are I will solve some of the questions that will be very similar to your assignment, so that whenever you will be solving the assignment, you will not feel completely new. Okay, so that are my duty. But before that, I always prefer to discuss some of the summary of the week, so that it will be easier for us whenever we are solving the questions. Okay, so by that, let's start the discussion. So yeah, from week 1 to week 8 we have discussed the basics or more theoretical knowledge about this neural networks. Okay, in week 9 we have discussed about this thing called NLP, that is natural language processing. Today we will be discussing about something known as convolutional neural network. Okay, so previous week we have discussed about NLP. So NLP is regarding the words. Okay, neural network applied for this learning of words. Okay, and today we will be applying this neural network for learning of images. Okay, so that neural network is known as convolutional neural network. But before that, it is important to know what is the convolution operation. Okay, so convolution operation is a mathematical operation that is applied in between two functions to achieve a third function. So it emphasizes the change of size that the second function is introducing to the first function. Okay, so that is convolutional operation. Okay, so how this convolution operation can be put on an image. Okay, put on an image, you can see this is an image. Okay, so image, we denote image by I. Okay, and we will be applying a convolution filter to it. Like I have told you, convolutional operation is between two functions. So let's say this is the other two function, f1 and f2. So we will be achieving the third function, that is f3. Now our f1 is nothing but the image. Okay, on which we will apply the convolutional filter. Okay, the convolution filter or the kernel, that is the f2. Okay, that we denote by k, and we will be achieving to the something called f3, that is a image after applying the convolution filter. Okay, now the image that you are seeing, this is a 2D input. Okay, what is a 2D input? 2D images are basically 3D, but to simplify it, we have shown it as a 2D image. Okay, so this is a 2D image. So 2D image, we have this two dimension. One is the height of the image, that is this, and second is the width of the image, that is this. Okay, so height of the image, you can say that is width of the image, that is I. Height of the image, okay, someone is joining. Okay, height of the image, that is j. Okay, so now we are applying this convolutional filter k. Okay, and this k has the dimension m cross n, means the filter has that dimension m cross n. Okay, now after applying this, we will be getting this. Okay, so this is our f1 function, this is our f2 function, and now after applying the f2 on f1, we are getting this f3 function. Okay, so this is convolution. Now to simplify it, let's do this by an example that will be more easier to you to understand. Like this is an input, okay, this is the input or I, okay, and this is our kernel, that is K. Now we will apply this kernel on this image, okay, and see how the kernel is influencing the image to get the third function, that is F3, okay. So that we will see. Now this is the kernel. Kernel is nothing but a filter applied to the image. Now this image or input, we have 1 2 3 3 3 rows and 4 columns, okay, and we are applying a 2 cross 2 filter on it, or 2 cross 2 filter on it. Now how we will apply the filter? We will just put the filter here and we will drag it side by side. Like first we will apply this filter here, okay. Now when we have applied this filter here, convolution operation we have to do, so we have to just multiply the pixel of this kernel to this image, okay. So AW, BX, EY and FZ, okay. So this is the thing, this is the first thing when we have applied the filter on this part of the image. Now we have to apply the filter on the next part of the image. Next part, what will be the next part? The next part will be this, okay, next part will be this, okay. So this again we will apply the convolution. Now after the multiplication, the result will be WB, XC, YF and GZ, okay. So this is the thing, this is the second thing. Similarly we will shift the filter to this position, okay, that is the third position, that this position. This position we will apply and this will be your result, okay. So this is the output. So input kernel and the output image, that is the F3 function, whatever, okay. So this is the thing. So that is how the convolution operation work, okay. So again there are three important things. One is the input, okay, second is the filter, that is the kernel, okay, and second, after applying the kernel to the input, we will be, okay, someone is joining. Okay, so after applying the this kernel to the input, we will be achieving our output, that is this output. So this is the convolution operation. Now the important thing what you have seen here in this formula, okay, if we try to apply our convolution in this way, we are not exactly influencing the middle pixel, okay. Like we can also this is a 2 cross 2 filter, but if we have this 3 cross 3 filter applied to this image, how we can apply this? We can either apply by this method, that is just you can put the convolution over there, but the second thing what we can do, we can do is we are interested in the middle pixel, okay. This is the middle pixel is our interest. So okay, someone is joining. So what we can do is we can apply our convolution like this, okay, like this. If we will apply, see, if we will do like this, what will happen is our output size will decrease, okay. You can see the input size here, that is 3 cross 4, okay, but the output size is 2 cross 3. That means the output size is decreasing. But if we apply our filter in this way, so our output size will be same, okay. So that is another way of applying the convolution, okay. So this is the thing about convolution. Now example, when the image when we can apply the convolution on the image, you can see this is a Taj Mahal image and we have applied this convolution filter, okay, 1 1 1 1 1 1. Now what it does, it is doing is it is blurring the image, okay. So after putting the convolution, this is blurring the image. We have this input, we have this kernel, and what is the effect? We are getting a blur image, okay. Similarly you can see in the second picture, this is the same picture, same input, but now we are applying this type of convolution, and by this what is happening is we are sharpening the image, okay, because you can see only in the diagonal, or only in the not in the diagonal exactly, or in the middle pixels only we are applying the values, okay. In the end or the starting pixel we are applying 0. So that is why what this filter is doing, it is sharpening the image. Similarly we can do this, that is detecting the edge. How we can do? If we can put a value in the mid pixel, okay, and other pixel if we can do 0 or 1. If we are doing 0 or 1, what will happen is we will detect the edges of the image, okay. So this is about convolution operation applied to the image, okay. So this is the theory about convolution operation. So is this slide clear to all of you? Okay, Okay, so let's move on to the next thing. Okay, so what is this feature map? Okay, so whenever we are applying this convolution operation, we are getting a output. That output is known as the feature map. Why it is known as feature map? Because we can apply so many filter on an image. Okay, so all the filter will give us a different output. That output is known as feature map. So we just slide the kernel over the input image. Each time we slide the kernel, okay, we get a one value of the output. Similarly, if we apply different type of filter, we will get different output. So the resulting output is called nothing but your feature map. Okay, so we will use this feature map in the upcoming this convolutional network that we can see. So this is known as feature map. So again I am repeating, whenever you are applying different type of kernel to an image, you will get different output. These output are nothing but known as feature maps of the image applying a particular kernel. Okay, so this is about feature map. Now whatever I have explained this, we are looking at a 2D input. Okay, but actually our image consists of 3D input. Okay, this all are 3D actually, but to make it simplify to you, we have introduced or we have explained by 2D image. But actually our image is a 3D image. Why our image is a 3D image? Because it has 3 channels, that is red, green and blue. Okay, RGB image. So our image is always a 3D input. Okay, now how we can apply a 3D how we can do this convolution operation on a 3D input. Okay, so same way we can just like we are doing on a 2D input, similar way we can do this convolution operation on a 3D input also. But the thing is, whenever you are applying one filter, that filter will be only at one channel. Okay, like this filter, whenever you will apply, you will first apply on this channel. Okay, similarly you will apply this convolution filter on the next channel. Similarly you will apply this convolution operation on the third channel. Okay, so by that way you can do the same convolution as you have done for a 2D, that you can do for a 3D input. Okay, so this is the thing. Now yeah, so I hope this is clear to all of you, what is a feature map and how you can do this convolution operation on a 3D input. So same thing, same way like we have done in the 2D, we will also do in the case of 3D. Only we have to what we have to do is we have to apply the filter on different channel one by one. Okay, so by this you can do this convolution operation on a 3D input also. Okay, now you have seen the three things, like right, you have seen image, you have seen kernel and you have seen the output. Okay, output, input, kernel and output. Now what is the dimension or what is the relation between the input, output and filter size? Okay, that we are interested in. Like I have told you, whenever we are applying the convolution in this way, our output size is decreasing. Earlier it was 3 cross 4. Okay, but after convolution operation our output is 2 cross 3, right? So we are and our kernel size is 2 cross 2. So after applying this, okay, someone is joining. Yeah, so after applying this 2 cross 2 kernel on this 3 cross 4 input, we are getting something output size 2 cross 3. So that means there is some relation between the output size, kernel and the input size, that we will see in this thing. Okay, so this is the topic, relation between input size, output size and filter size. Now what is the relation? Now let's see the input image. Okay, input we have dimension, the width of the image is W1, the height of the image is H1 and the depth of the image, that is D1. Okay, so this is the about the input image. Now what about kernel? Kernel, we have a kernel of we have a kernel of size f, that is f cross f. Okay, the kernel is of size f cross f. This is the size of the input, that is W1 into H1 into D1. Okay, and this is your filter size, and we are applying k filters, number of filters is k. Okay, so this is the thing. Now what will be the output size? That is W2, H2 and D2. So D2 we will see later, but in this slide what will be the W2 and H2? The W2 will be W1 minus F plus 1. F is the size of the kernel. Okay, so that will be W2. Similarly, what will be the H2? H2 will be H1 minus F plus 1. Okay, so this is the simple formula. Now the next thing is padding. Okay, so whenever we are whenever we are applying this filter in that way, in this way, that is we are influencing, or we want our pixel of interest is the middle pixel. So what will happen is, this pixel we are not able to apply a convolution. Okay, so padding operation will help in that cause. Okay, so padding means we are this is our original image, the one in the white or no background. This is the original image. Okay, and what we are doing is we are giving a padding a padding above the original image. So this is the padding. So now what will happen? Now our formula will be enhanced by this. Okay, now earlier what we are seeing is, earlier our size is decreasing, like W2 will be becoming W1 minus F plus 1. Okay, similarly H2 is becoming H1 minus F plus 1. But after giving the padding, there will be increase in size. Okay, so how the size will be increased? The size will be increased by 2p. Okay, so W2 will be W1 minus F plus 1, as it is the previous formula. But here, as we are applying this padding, now our W2 will be increased by 2p. Similarly, H2 will also be increased by 2p. Now there is a concept of stride. Now up to now, whatever the convolution operation I have shown you, what we are doing, like we have this kernel. Okay, 1 2 3 3 cross 3 kernel. So earlier what we are doing is, we are just putting kernel like this. Okay, and we are dragging it side by side. Like in the next step, our kernel will be like this. Okay, next step our kernel will be like this. Okay, like this will be our next step. Okay, but it can happen that we are not, in the next step we are not interested to slide it by one step. We are interested to slide it by two step. Okay, in that case, this thing is known as stride. So earlier when we are doing this, our stride was 1. That means we are shifting the kernel only by one interval. But if we desire to shift a kernel by s interval, then our stride will be s. Okay, so after introducing this stride, our formula will be modified like this. W2 will be equal to W1 minus F plus 2p divided by s. As we are shifting our kernel to that much stride, so that is why we will be dividing by s. Okay, our dimension will get smaller. So there are three operations side by side. First, when we do not have any stride, or a stride is 1, and when we do not have any padding. This is the formula. Now when we are introducing a padding, our output size will be increased by 2p. Now when we are introducing this stride, our output will be divided by s. Approximately, this plus 1 will be there, but approximately our output size will be decreased by s. Okay, so that is the three things. Now the last thing that is remaining, until now what we have discussed regarding the width of the image and the height of the image, but we have not discussed about the depth of the image. So depth of the original image was d1. Okay, now we are applying how many number of filter? We are applying k number of filters, right? We are applying k numbers of filter. So as we are applying k number of filters, so our depth of the output image will be equal to k. So that is d2 equals to k. So ultimately we need to remember these three formulas. Our depth of the output image will be equal to number of filters applied, that is k. The width of the output image will be equal to W1, that is width of the input image, minus the size of the filter f, plus 2p. P is the padding, and s is the divided by s, as is the stride, plus 1. Similarly in case of H2 equals to H1 minus f plus 2p divided by s plus 1. Okay, so this is the relation between your input size, output size, and the filter size with stride and padding. So these are the three formulas you always need to remember regarding this convolution operation. Okay, so is this clear to all of you? Clear, right? Okay. So I hope this formula is clear to all of you. At least you need to memorize this formula, because many question will be coming from this formula only. Okay. So they will give you an input, they will give you filter size, this padding or padding, stride, etc., and they will ask to calculate the output size. Okay. So I hope by this three formula you can calculate all the questions. Okay. So this is the thing. Now after this, now whatever we are doing this convolution operation, but our subject name is deep learning, right? Deep learning is neural network. Now how this convolution operation will help us in this neural network? So what is the connection between this operation convolution and the neural network? And second, we will try to understand this by considering the task of image classification. Okay, so the task is image classification, and by this task we will see how this convolution operation that we have shown in the previous slide will work with this neural network. Okay, so earlier whenever we have this machine learning, what we are doing is to classify an image, we are just learning meaningful we are just extracting the feature with the help of a supplied kernel. Okay, we are not learning any kernel, we are giving the input image, we are supplying one type of kernel, and by that we are getting some feature, and after on the top of that what we will do, we will just be applying our machine learning algorithms, and we are achieving the output prediction. Okay, that is the approach of a machine learning problem. But as we are learning about neural network, so in neural network, in machine learning, you have to give the kernel on your own and learn the feature first. But in but in neural network, what we can do, we can learn this kernels. Okay, that is the difference between the machine learning that we apply earlier and deep learning. Deep learning, we can learn the kernels. Okay, we just need to give an image and we can learn these kernels. As we can learn these kernels layer by layer, at the last layer or at the output layer, we can get the classification of an image, like this is a car, bus, monument or flower. So at the last layer we can get this is a monument. So in neural network approach, in machine learning approach, what we have to do, we have to give this kernel by our own, and we have to give this kernel on our own, and we have to learn the feature first, and after we learn the feature, then we are applying a machine learning algorithm, and our algorithm will predict the output class. But in neural network, what we can do, we can learn the kernel. Okay, we do not need to supply this kernel on by our own, but we can learn this kernel. Okay, this how we can learn this kernel? We can learn this kernel as the weight of the neural network. Okay, we will assume that these kernels are nothing but the weight of the neural network, and by backpropagation we will learn this weight, and once we learn this weight, we can predict what is the output class. Okay, so that is the difference between the machine learning and the deep learning. Okay, so this is the thing. Instead of using handcrafted kernels, in machine learning we are using this handcrafted kernels, such as this edge detector. We can learn meaningful kernel filter in addition to learning the weight of the classifier. Okay, so yes, we can simply by treating this kernel as the parameters. Okay, so just I have told you what are our parameters. Our parameters are weight and bias in a neural network. So just by treating this kernels as the weight or parameters of the neural network, we can learn this kernel itself, and then we do not need to supply the handcrafted kernel. So such type of network is known as convolution neural network. Okay, so what we are learning the weights. These weights are nothing but a kernel, and what this kernel will do, this kernel will do one set of convolution operation, okay, to learn the output. So that is why this type of neural network are known as convolution neural network. Okay, so this is the thing. But the question is how this neural network are different from the original neural network or the feed forward neural network. Okay, so we have till now we have learned about the feed forward neural network. Okay, so the question is the convolution neural network different from feed forward neural network? Is there any difference between the convolution neural network and a feed forward neural network? So yes, there are some difference about the convolution neural network and feed forward neural network. So this is an example of feed forward neural network. So in feed forward neural network, what you will do is you will be supplying the input, you will be supplying the hidden, you will be framing your architecture such that there will be input layer, this is your input layer, there will be many hidden layers, and there is a output layer. Now the thing is, the input, each neurons of the input will be connected to each neuron of the hidden layer. Similarly, each neuron of the second hidden layer will be connected to each neuron of the third hidden layer. Similarly, each neuron of the last hidden layer will be connected to each output. Okay, so that is feed forward neural network, means each neuron will be connected to every other neuron of the next layer. So this is feed forward neural network. But how is this thing different in the case of our convolution neural network? In convolution neural network, what we do is we do something called sparse connectivity. That means we reduce the number of sparse connectivity will reduce the number of parameters. But what is this sparse connectivity? Sparse connectivity means earlier in feed forward neural network, each neuron of the input layer is connected to every neuron of the first hidden layer. So, similarly, each neuron of the first hidden layer is connected to each neuron of the second hidden layer. But in convolution neural network, we are not connecting each neuron of the input layer to each neuron of the first hidden layer. We will connect some neuron to neuron of input layer to some neuron of hidden layer. Okay, so we will do like this. So by doing this is known as sparse connectivity. Okay, earlier we have dense connectivity. That means each neuron is connected to, like you can see in this image, this is the red neurons are input layer neurons. This blue neurons are neurons of the first hidden layer. You can see that each red neuron is connected to each blue neuron. But in this image, you can clearly see that each neuron of the input layer is not connected to each neuron of the hidden layer. We are only first, second, third and fourth. Only four neurons are connected to the first neuron of the hidden layer. Similarly, second neuron of the hidden layer, again we have some connection, like third, fourth, and fifth, sixth, seventh and eighth. Third, fourth and seventh and eighth is connected to the second neuron of the hidden layer. So all the input are not connected to all neuron of the hidden layer. So this is sparse connectivity. Why we are doing sparse connectivity? To reduce the number of parameter of the model. So this is the explanation. Why we are doing this? Because if we will just connect each neuron of the hidden layer to each neuron of the input layer, so we will have so many connection. As our connection will increase, we will have so many parameters. So many parameter we do not want, because if we will have so many parameter, to train the neural network, we have to learn all these parameters. So that we do not want. So that is why we are applying this strategy, first strategy known as sparse connectivity. That means we are not connecting each neuron of the layer to each neuron of the next layer. So that is sparse connectivity. But now the question might arise, as we are not connecting each neuron of the above layer to each neuron of the previous layer, there can be a loss of information, right? That can be a question, because we are not connecting each neuron, so there can be a loss of information. That can be a question. But as we are doing this deep neural network, what will happen in this? You can see this the two highlighted neuron x1 and x5, like x1 and x5 do not interact in layer 1. Okay, in layer 1 these are not interacting. This is our layer 1. Layer 1 is hidden layer. Okay, layer 1, this is the layer 1. You can see this x1 and x5 is not interacting in L1 layer. But as we go to the next layer, you can see in this second layer, you can see this G3, this x1 and x5 are interacting. Like x1 is interacting to this neuron, x5 is interacting to this neuron, and in this layer, this two neurons are again, or the information of this two neuron is passed on this neuron. So this G3 has the effect of both x1 and x3. So that means there is no loss of information by this sparse connectivity. Okay, this is the first strategy that we apply in a convolution neural network. We have the second strategy. Second strategy is known as weight sharing. So this strategy you must have remembered from your this PCA principal component, sorry, not PCA, in the autoencoder also we have applied this weight sharing. So as we have the number of parameter increases, here we are only seeing for 3 layers, but in our deep neural network we will have 16, 20, 22 or even like 100 of layers. So in 100 of layers our parameters still increasing. Even we are applying this strategy of sparse connectivity, still our parameter will be very large. So to deal with that, we use this strategy known as weight sharing. So what we do in weight sharing, we will have same parameter, we will initialize same number of parameter for different neurons. Like here you can see we have this we have this 3 hidden neuron, and we have here also 3 hidden neuron. Now you can see the pink weights, this pink weights here, pink weights are here also, and pink weights are here also. That means we are sharing the weight. By sharing the weight, what if we are not sharing the weight, then we will initialize different weight for different connection. But as we are sharing the weight, we are applying same weight for 2 or more than 2 neurons. So by that we are again reducing the number of parameters. So these are the two strategies that we apply in convolution neural network that was not present in our feed forward neural network. Okay, so this is the thing. So is this slide clear to all of you? What is the difference between feed forward neural network and this convolution neural network? Okay, so again I am repeating, feed forward neural network and convolution neural network, even convolution neural network is also a feed forward neural network. Only difference is if we are if we are we want to apply the deep convolution deep neural network, what will happen is we will have so many number of parameters. Okay, so many number of parameters if we are applying to an image input. Okay, so to deal with that we apply this two strategy. One is the sparse connectivity, one is the weight sharing. Sparse connectivity means earlier in feed forward neural network, each neuron of the previous layer is connected to each neuron of the next layer. But in sparse connectivity we are only connecting some of the neurons of the input layer to some of the neurons of the hidden layer. Okay, by that we are decreasing the number of parameters. Second way is weight sharing. Earlier in the feed forward neural network we are initializing each connection to different weight, but in weight sharing what we will do, for some neurons we will be applying same weights. Okay, so by that we are again decreasing the number of parameter to be learned. Okay, so this is the concept. Now to move on to this, how a convolution neural network look like. Okay, so this is how the convolution neural network look like. This is the input, then we will have many convolution layer, then we will have something called pooling layer, then again convolution, again pooling. Like that our layer by layer our story will run forward, and then at last we will have fully connected layer. Like convolution layer will be in the first, but at last what we will always do, we will always have a fully connected layers. Okay, convolution neural network does not mean that each layer will be a convolution layer. At last we will be giving some fully connected layer. In fully connected layer, all the neurons of the previous layer will be connected to all the layers of the all the neurons of the previous layer will be connected to all the neurons of the next layer in the fully connected regions. Now the question is, what is this pooling? Okay, so whenever we are applying this convolution filter, what will happen is we will have so many number of feature map. Like in this convolution layer you can see we have 1 2 3 4 5 6 convolution filters, right? So we will have so many feature maps. Okay, so to decrease the information, what we will do, we will be doing this operation known as pooling. What does pooling do? Pooling also has some kind of filters like convolution filters. But what does pooling do? Convolution means each pixel of the filter is multiplied to each pixel of the image. But in pooling what we do, we just take a window. Like you can see this is an input. Okay, now we are applying a pooling layer. Now this is the pooling layer. Okay, this is the pooling layer. That means we are applying a 2 cross 2 pooling layer. The type of pooling we are using is max pooling. That means we will be just focusing on this, and as we are using max pooling, that means we will only take the pixel that has maximum value, because we are doing this max pooling. So 1458 we will only take what we will only take, as we are doing max pooling, so we will only take this 8 pixels. So this is this. Okay, now we are applying, we are not taking the stride as one, we are here we are not taking stride like this, like one. What we are doing is, again we will apply this pooling layer, pooling filter to this layer. That means as we are only done with this 2 cross 2 2 cross 2 size of the input, now we will be focusing on next 2 cross 2 size of input. Now here also we will take the maximum pixel. So maximum pixel here is 4, so our next value will be 4. Similarly, we will be applying this pooling on this layer that is not yet touched, so the maximum value is 7, so we will write the 7. Similarly, we will apply this pooling to this, and as we are doing maximum pooling, so 5 will be our maximum pixel, so 5. So after pooling, we are achieving this output. Okay, now instead of doing this max pooling operation, you can also do something called average pooling operation. So average pooling, how we can do average pooling? You just take this window and you will do the average of all the pixel that is in the window. So if I am doing average pooling, our average will be 1 plus 4 5, 5 plus 5 10, 10 plus 8, that is 18. Okay, 18 divided by 4, that is 4.5. So here the value will be 4.5. Similarly, if we do average pooling, our value will be 336, that means 10. Okay, 10 divided by 4 is 2.5. Our value here will be 2.5. So that this operation is known as pooling operation. Okay, now how to train a neural network? We will be applying the same thing that we have learned again and again, that is backpropagation. Okay, but backpropagation now we have to apply by thinking about the sparse connection. Okay, here you can see this gray connection. This gray connection means we do not have connection in this neuron, like B is not attached to M. Okay, like this. So that is a gray connection. So in this connection you can't apply this backpropagation, but the connection with connection with the colors, in that connection you can apply the backpropagation, and rest is the same thing. Backpropagation, you have to do the dl by whatever the input. Okay, dl by dx. Okay, that you have to do, and you can do the backpropagation, and by this you will be learning the now you will be learning the filter pixels. Okay, so by that you can just train the CNN. Okay, so this is the thing how you can train the CNN. Okay, so this is the thing, a CNN can be implemented as a feed forward neural network. Same thing, wherein only a few weights and colors are active, like only a few weights that are in colors are active, others are not active. So whenever you will be doing backpropagation, the weights which are not active, it will be giving 0. Okay, the rest of the weight in gray are 0. Okay, thus we can train a convolution neural network using backpropagation by thinking it as a feed forward neural network with sparse connection. So only difference about the in training is, here we have sparse connection, so sum of the dl by dx will be coming 0. Okay, so that is the only difference in training the CNN. So is it clear to all of you how a neural network looks like? Clear, right? Am I audible? Okay, so let's move on to the next thing. Now as we have introduced CNN, now we should see some of the applications of CNN. So there are many success story on this ImageNet. So there was a competition called as ImageNet large scale visual recognized competition. Okay, there we have like million of image and we have 1000 classes. Okay, and competitors were asked build different neural networks so that it can classify the it can do this image classification. Okay, so it was started from 2010. Okay, so in 2010 and 2011, these are the two architectures. So this is built on shallow networks. Shallow networks means they are only applying this machine learning. They are not learning the filters. They are just handcrafting the kernels, and on the top of it they are applying the classification algorithm or the machine learning classification algorithm, and by that they are classifying the classes. Okay, so earlier they have these are the errors. So earlier they have errors 28.2%. That means if they have this 1000 image, they are getting the error for 282 image. Okay, and they are only getting success for like 818 image. Okay, so this is the thing. This is the story about shallow network. Okay, these are the story about shallow network that was applied in 2010 and 11. Okay, after that our neural network came into picture from 2012 to 2014, and we have introduced this different network. One is known as alexnet, one is known as zfnet, one is known as vgg. Okay, alexnet, it has 8 layers, and the error decreases from 25.8% to 16.4%. Okay, by alexnet. Then there was a term known as zfnet. That architecture was introduced. This also has 8 layers, but now the error got decreases from 16.4% to 11.7%. Okay, after that they have introduced a network known as vgg. VGG19 has 19 layers, and the error decreases from 11.7 to 7.3%. After that this two architecture came into picture. Okay, these have more number of layers. One is googlenet, that was introduced by Google, and after that Microsoft introduced this resnet. Okay, this googlenet also has 22 layers, and the error decreases from 7.3% to 6.7%. And when this Microsoft introduces this resnet, the classification error reduced to 3.57%. Okay, so these are the different success story on the ImageNet. Okay, now these two are machine learning networks. So here these two we will not learn, but we will see the architecture of alexnet, zfnet, vgg, and this googlenet and resnet. Okay, so let's start with this alexnet versus zfnet. Okay, so this is the this is the architecture of alexnet. So alexnet, we have this 8 layers. Okay, 8 layers. Whenever we are talking about layers, so layers does not include this pooling layer. Why layer does not include this pooling layer? Because pooling layer has no parameter. Remember, parameter means we are only learning the pixel values of the convolution kernels. Okay, not the pooling kernels. Okay, so that is why the parameters will only be present in this convolution network as well as convolution layer, as well as this fully connected layer. So alexnet as well as zfnet, they have 8 layers both. So these are the layers. This is the first layer, this is the second, third, fourth, fifth, sixth, 7th and 8th. So these are the 8 layers. Out of 8 layer we have 1, 2, 3, 4, 5. We have this 5 convolution layer, and we have this last 3 are the fully connected layers. Okay, this is about alexnet. The filters that they use here, the first convolution filter that they use was of dimension 11 cross 11. Okay, but in zfnet, if I just draw the difference in zfnet, the convolution filter they have introduced first was 7 cross 7. Okay, so that was the first difference. After that, this layer is same, this layer is also kind of same. This layer is same, but now we have 512 kernels in this layers. Okay, in this convolution layer. Similarly, in here earlier we have 384 convolution filters in this layer, but in this zfnet we have 1024 convolution filter. Similarly, in the next layer, earlier we have 256 convolution filter, now we have 512 convolution filter. So these are the difference. First difference is this. First we have filter size of 11 cross 11 in alexnet, and here we have filter size 7 cross 7. And then in this 3 layer we have this difference. First we have 384 convolution filters in this 1 to 3rd layer. here we have in this third layer we have 512 convolution filters. Second, in this alexnet we have this 484 how much it is, yeah, we have 256 convolution filter. Here we have yeah, first we have 384 convolution filter, in third layer we have 384 convolution filter in alexnet, and here we have 512 convolution filter. Here we have this 384 convolution filter, and here we have 1024 convolution filter. In alexnet we have this 256 convolution filter, here we have 512 convolution filter. So these are the main difference of alexnet and zfnet. So the logic here is, in zfnet we are increasing the number of parameter but by 1.45 million. Why we are increasing? As we will have more number of parameter, our neural network will learn well and our error will decrease. So that is why the error in this alexnet was coming 16.4%, whereas then in this zfnet our error decreases to 11.7%. So that is the difference between this alexnet and zfnet. Okay, more details you can just refer to a lecture, but this is the summary. Okay, and then about VGGNet, after the alexnet and zfnet zfnet we we have this network known as VGGNet, and here we are talking about VGG16. VGG also has a variant called VGG19, that means it has 19 layer, but here we are only looking about 16 layer. So what does this VGG doing is, the kernel size it is keeping fixed, that is 3 cross 3. Earlier we will have different size of kernel like 11 cross 11, 7 cross 7, then 3 cross 3, 5 cross 5, like this. But here throughout the network we have this kernel size 3 cross 3. Okay, so total number of parameters in the non fully connected layer, that means up to this, that is 16 million, and total number of parameter in the fully connected layer was 122 million, and most parameters are in this fully connected layer, that means that is 102 million. Okay, so by introducing this, again our error decreases to, okay, this is the for a 19 layer, but VGG16 our error decreases to some amount. Okay, so this is the concept. Okay, so main difference between alexnet, zfnet versus this VGGNet. VGGNet we have this kernel size 3 cross 3 throughout, but here the kernel size is changing from layer to layers. This is the main difference from alexnet, zfnet to VGGNet. Okay, so this is the thing about this tree architecture, that is alexnet, zfnet and VGGNet. Okay, so is this clear to all of you? Is this clear? Okay. So after this we will be learning about this two architecture, that is googlenet and resnet. Okay, so what is the idea between the behind the googlenet? Earlier in all this network you are seeing like alexnet, zfnet as well as this VGGNet, what we are seeing is in a convolution layer we are in a convolution layer we are applying same size of filter. Like in this convolution layer we are only applying 3 cross 3 filter, in this convolution layer also 3 cross 3 filter, like that. So each convolution layer we are applying same filter. Like in this convolution layer we are only applying only 3 cross 3 filter. So this is the thing. But the intuition is, why not in the same convolution layer we can apply different type of filter. Like in same convolution layer we can apply this 1 cross 1 filter also, 3 cross 3 filter also, as well as 5 cross 5 filter also. Okay, so this is the question. So yeah, we can apply this. So this is the main idea behind this googlenet. That means in the same convolution layer we are applying different kind of filters. Okay, this is the main idea behind this googlenet. Okay, so this type of module where many convolution filters are applied in the same convolution layer, this type of module is known as inception module. Okay, that means many convolution operation is operation are applied to a same convolution layer. So this type of module is known as inception module. Okay, so earlier in each layer, earlier we are applying this layers in a series wise, right? Like this 3x3 convolution layer, we are first doing the operation for this layer, and then we are doing the operation for this layer. Okay, but in this inception module, what we are doing is we are applying the filters in parallel. That means we will do many operation in the same layer in parallel wise. Okay, so this is more, this diagram I think is more clear. So what we will do is we will we will apply this 1x1 convolution, then 3x3 convolution, then 5x5 convolution, then 1x1 convolution, all in parallel. Okay, same layer and all in parallel. So this type of module is known as inception module. Earlier what we are doing, we are applying this filter series wise. That means first filter we are applying, and then in the second layer we are applying a different filter. But in this inception module, in a single layer we are applying many filters. So that this type of module is known as inception module. Okay, so what has been seen is, as we are applying different kind of filter, our depth is increasing. Because depth is equal to size of the filter. Okay, d of the output image is equal to size of the filter, right? So there was a problem earlier that as we are applying so many filters in a single layer, our depth was increasing. So they came out with this 1x1 convolution. Okay, so as we are applying 1x1 convolution and reduce the d from d to d1, what will happen is our number of computation will decrease. So earlier, as we are in a single layer, we are applying so many convolution, we have this this number of computation, that is O f cross f, because f cross f is the size of the kernel, and d is the depth of the kernel. Okay, but now what has been thought is, what we will do, we will reduce the d to d1. Okay, such that this d1 will be lesser than d. And then what we will do is, before applying this convolution operation, we will first apply a 1x1 convolution. 1x1 convolution means we are just changing the value of a pixel. That is what we mean in 1x1 convolution. But by doing this, what is happening, we are just decreasing the number of parameters. Okay, so this is the idea behind googlenet. So this is the architecture of the googlenet. Here you can see this thing, this is the convolution layer, that means simple layer as you have seen in alexnet or zfnet. Then we have a max pooling layer, then again we have a convolution, then max pooling. Here this layer is the inception module. Inception module means in this layer so many filters are there. Okay, so then we have this second inception module, then we have this third inception module, fourth inception, fifth inception, and this we have this sixth inception. So there are 6 inception module in the googlenet. Okay, so if I compare about googlenet versus alexnet, this googlenet has 12x less parameters than alexnet, and second, it will have 2x more computation. As we can see in this image, we are applying a convolution after we are applying a 1x1 convolution, and after that we are applying this filter. So what will happen is, our number of computations will increase. But what is this googlenet doing is, it is doing some kind of modification in the fully connected layer. Okay, we are applying this dropout strategy. That means we are only taking few neurons. Okay, we are applying this dropout strategy of 40%. That is why when the neurons are connected from this last convolution layer to this fully connected layer, we will have 12x less parameter than alexnet. So only thing you have to remember is, googlenet introduced this inception model. What is this inception model? Inception model means in a single convolution layer we are applying different type of convolution filter at once. So this is the idea you have to remember. Okay, then we are moving on to this architecture known as resnet. Okay, now up to this googlenet, the number of layers you can see in this image, number of layers we have only this 22 layers, not more than that. But what this Microsoft introduced is something known as resnet. This resnet has so many layers. Like resnet has some variants like resnet 50 is there, and also resnet has some variant called resnet 152. Okay, like this layer, resnet has 152 layers. So if we will have so many, okay, so what is the idea behind resnet that you have to understand. Now what the makers of resnet thought is that if we are successfully able to train a shallow network means not that shallow, like this 19 layer 22 layer. Now if we are introducing this convolution layer in between this shallow networks, we can get more accuracy or less error. So that is the idea of the resnet. Okay, so again I am repeating, up to googlenet we have this shallow layer means not that shallow, like 16 layer 19 layer 22 layer, like that. Now what the makers of resnet thought that if we can introduce many convolution layer in between the shallow layers, our neural network will perform better, okay, perform better than previous network, right? But actually the case was not that. Actually what happened is that as we are introducing so many stack layer in between our shallow network, what is happening is how our neural network learn from layer to layer by constructing an abstract of the input. Okay, so by that only our neural network learn from layer to layer. As we are introducing so many stack layer in between our shallow network, what is happening are in the top layers the abstract learning is not the abstract learning, the network was not able to learn so many abstracts. So that was the problem that is happening with this idea. So now what the makers of resnet thought, they came with this idea. Okay, what is this idea? This is the input, okay, and this are the layer, like this is the first convolution layer, this is the next convolution layer. So in general the abstract that we are getting after the second convolution layer was hx. Okay, but as if we introduce so many stacked convolution layer in between this two layer, what will happen is this representation will not be that strong. Okay, this representation will be very weak. So what the makers of resnet thought is, at this layer if we can again introduce the input, okay, if we can again introduce the input, so earlier our neural network was learning this hx on the basis of only this fx, okay, but if we again can introduce the input again, so our neural network will learn better. So by that they came with this idea known as resnet. So again I am repeating, first what they thought is, if our neural network that is shallow layers, that means 16 layer 19 layer 22 layer, if it is learning better, if we can introduce so many stack layer in between the shallow network, our neural network will perform better. But then they experimented it and they found the result worse. That means they did not achieve better accuracy or less error by this concept. So what they came up with the theory is, as we are applying so many abstract layer in between two convolution layer, our abstract learning is not happening that much stronger. Okay, so what they came up with the idea, at this after some convolution layer, if we can again give the input again to this abstract representation, our neural network will learn better. So by this they come with the idea of this resnet, and you can see this resnet, they have introduced 152 layer. Remember this googlenet was only 22 layer, but what they have done, in between two layer they have stacked so many layers in between two convolution layer, and they came out with this architecture known as resnet. And this resnet has 152 layer, and now the error decreases to 3.57%. That means in 1000 image, if I classify it in 1000 image, they are getting error like 4 images we are getting error. So that is even better than human. Like human, if you will give 1000 image to a human, even he will do error like 10 15 images he will do error. But This resnet was so successful that the error decreases to 3.57%. Okay, so this was the concept of googlenet and the resnet. So what was the concept of googlenet? The concept of googlenet was nothing but inception module. And what was the concept of resnet? Concept of resnet is to supply the input after to supply the input again to the abstract representation, so that our neural network will learn better. So that is the idea behind the resnet. Okay, so is the concept clear to all of you? Am I audible? Am I audible? Hello? Okay. Okay, so this is the concept of neural network. Okay, and after this we will see some of the things called pattern recognition. What is this pattern recognition? Pattern recognition is a field of this computer vision that deals with this neural network. But in pattern recognition, what we are interested, to know the things that how a neural network is learning the image, or how a neural network is learning to classify an image. That means we will see each network, we will see each neuron, and we will see which neuron is learning more and which neuron is learning less. Okay, by that what we are trying to achieve, we are trying to achieve a pattern. Okay, and by this pattern we will say that we will do is we will classify the output of the image. Okay, so that field is known as pattern recognition. Okay, now there are some of the codes that I will show you. So one of the experiment is a convolution experiment. So what is this? Occlusion sensitivity analysis for this CNN. So what is this occlusion sensitivity? Occlusion sensitivity is used to visualize which region of image are most important for classification. So you have this image, okay, and now we are doing something called pattern recognition. Means we will see the image, we will see which patterns are important in classifying the image. Okay, and this this experiment is known, this experiment or this analysis is known as occlusion sensitivity experiment. So what we will do, this is our libraries that we will import, and we are importing the model known as VGG16. Okay, VGG16 we will import. We will load an image, like any image you can load from the internet. This is how you can load an image, just you by giving a URL. So where I have given the URL, yeah, this is the URL. Just giving a URL of the image, you can load the image. Then what we are doing is we are defining the occlusion parameter. What is the occlusion parameter? Occlusion parameter first is patch size. That means what you will see is you will just take a window of the image, and what we will do, what you will do is you will okay, what you will you will do is in that patch size you will be interested that if I just move the patch from one position to next position, what is the drop in confidence. So earlier if you block one patch, so there will be some drop in confidence. Then we just shift the patch from this position to this position, and now again we will see what is the drop in confidence. So by that we can clearly see that in which patch, if we are blocking this patch, we will be getting more drop in confidence in this patch. So that is the occlusion experiment. Occlusion means if one object is behind another object, so that is known as occlusion. One object is behind another object, so you cannot see the second object behind the first object, so that is occlusion. So in this occlusion sensitivity experiment, what we do is we take an image, we block this pixel, this certain pixel of the image, and we see what is the drop in confidence in classifying the image. Second, we just shift the window or shift this occlusion patch to next position, and then again we see what is the drop in confidence. Okay, by that we can see which patch is the most important in classifying the image. So that is occlusion sensitivity experiment. Okay, so this is the code. Yeah, just load the image and load this VGC16 model, and now these are the two parameter. One is the patch size of occlusion, that means which what is the size of the patch for which I am interested in this occlusion experiment. Second is the stride means how much step you want to push the push the occlusion patch. Okay, now the stride here I am taking is 16, that means step size for sliding the occlusion window. So that is the stride. Now just I am running the occlusion experiment, and I will do this for epochs. How many epochs are given? So this is the thing, epochs. Where is the epochs? Yeah, these are the steps for which I have, yeah, these are the steps for which I have given this occlusion experiment. Okay, so just you run with a certain number of epochs, and this is the output. Yeah, this is the occlusion heat map, you can see. So at this patch of the image is the most sensitive to occlusion. That means if this patch of the image is like this patch of the image is blocked, the drop in confidence for classifying will be 0.8. Okay, earlier if our confidence in classifying this line was 1, if I just block this patch, so our drop in, or you can say precisely, if this red patch I block, our drop in confidence will be 0.8. That means earlier if our success was 100%, our success in blocking this patch, our success will remain only 20%. So that is the occlusion experiment, occlusion sensitivity experiment. Okay, so this is the first task that you can do with this pattern recognition. Okay, so this is the result. So is this thing clear to all of you? So is this thing clear, what I have done? Is the code visible to all of you? Yeah, code was visible, right? So you got what we did in occlusion sensitivity experiment, right? We just find out that which part of the input or which region of the input is most sensitive to our classification result. Okay, what we do in occlusion experiment is, or occlusion analysis experiment is, we just block different patches of our image. Okay, and we see for which patch we are blocking, our confidence level is decreasing. Okay, for which occlusion patch or which patch we are occluding, for that what is the drop in confidence, and we are interested to find out maximum drop in confidence for a particular occlusion patch. Okay, so that is our first thing. Now what we will do, now we can just see this, that is image reconstruction. Now what I have told you, how our neural network learn is, our neural network learn by each convolution filter, right? For first layer our neural network will learn something. For second, after applying second convolution, our neural network will learn different feature map. Our third layer, our neural network will learn a different feature map or the different abstract of the image. So what we do in this image reconstruction embedding is, we just take an image, we see for each convolution layer, how our abstract representation is looking like. Okay, so again we will be using here what type of neural network, yeah, we are using this VGG19 neural network. Okay, again we will load the model as well as we will load the input. Okay, and now you can see the result. This is the result. Okay. Yeah, this is the result. Yeah, in the layer 0, that means the first layer, this is the abstract representation that we are getting from the first layer. This is the layer 1, the abstract representation we are getting in the layer 1. Similarly layer 2, layer 3. Similarly, as we go from the initial layer to the final layers, our abstract representation will be very blurred. So this is the abstract representation that we are getting after so many layers. Okay, so that this task is known as image reconstruction embedding. That means we are reconstructing the image at each layer of the convolution. Like in this, you can see in this 31 layer, you can see the we are getting very blurred image, very blurred abstract representation of the image. Okay, so this is the thing. This is the second task. And the task also we can see these things like, yeah, we can see these things like, yeah, we can see this thing, there's a trend going on, you all know, that is givelify the image, right? You just give an image to the chat GPT and it will givelify the image. So that can also be done by our neural network code. This is known as something known as neural style transfer, or NST, neural style transfer. So what we will do, we will give two kind of image. One is the input image and another one is the style image. Okay, this two image if we will give, we will achieve the third image. Now how is this neural style transfer work is that, we will be transferring the same image, we will take one neural network and we will apply, we will run the, we will give it, we have two images, right? One is the first one is the input image, okay, and second one is the style image, okay, and we will be achieving the third image. Okay, so what how this work is that, we will pass this input image as well as we will pass the style image to a same neural network. Okay, same neural network, like this is a neural network, we will be passing the input image as well as the style image to the same neural network. Now we will focus onto a layer. On the same layer you will be getting some properties of the input image and some property of the style image. Okay, from this layer we will reconstruct the image, like we have seen in the previous code how we can reconstruct the image. So by that, what we will do, we will just transfer the style, we will just transfer the style of the style image to the input image and we will get the output image. Okay, so this is the concept. So you can see here, this is the, yeah, this is the thing, this is the Harry Potter character, okay, the principal Dumbledore, and this is the Mona Lisa painting. Okay, so this is the neural style transfer. This is known as neural style transfer, and we have two image. This is the input image, and or this is the input image, also known as content image, and this is the style image. Okay, so what we are doing, we are providing an input image, we are providing a style image, and we are getting this output image. You can see the clear difference. This is the input image, okay, and this is the style, that is Mona Lisa painting style, and now we are getting output like the style image. Okay, so this is how you can do the neural style transfer, or NST. Okay, so this is the thing. Now you can also try this with this Ghibli image, that is a trend going on. So you can just provide an input image and you can provide the style image as the Ghibli image, and you will be getting the output as a Ghibli style image. Okay, but only thing is that you have to just like epochs, you have to give or iteration, you have to give so many iteration, like if you will do 1000 iteration, so your output image will be more likely to your this more likely like your this style image. Okay, so this is the thing. So this is known as neural style transfer. So you have this two image, one is the input image or the content image, and you have the style image, and you will get a output image that is the style embedded to the content image. So this thing is known as neural style transfer. Okay, another code I want to show is the convolution operation. That is a very simple code, but still it is very useful, especially for this edge detection type of thing. So this is the convolution operation. Okay, so convolution operation, you will be okay, this code, I think it will take some time to load. Yeah, this is the code. So convolution operation, like I have shown you in your theory, convolution operation, you will apply different kind of filters to the image. Okay, someone is joining. Yeah, so convolution operation, you will apply different type of filter to your image. So this filter will sharpen your image, this filter will detect edge of your image, and this filter will NP1, that means it is a 5 cross 5 yeah, it is a 5 cross 5 filter. Okay, and what this filter will do, all the elements of this filter is 1. Okay, so by this filter, what it will do, it will blur the image. So we have this 3 kernels, and we have this 3 input images. One is a monument image, one is a mountain image, and one is the animal image, and you can see the result. Okay, yeah, you can see the result. This is the original monument image. We have given a blur filter, so this is the monument blur. We have given the sharpen filter, and this is the sharpen structure of the monument. And lastly, we have given a filter for edge detection, so this is detecting the edges. Similarly, we can do for this mountain image. Okay, mountain image, again we have applied the same blur filter like the one in this monument. We have applied the sharpen filter. This is the sharpen image, and we have applied the edge filter, so this is the edge detected image. Similarly, we can also perform for this animal. You can see this is the original image, this is the blurred, this is the sharpened image, and this is the edge detected image. Okay, so this is the thing. Yeah, this is the thing. Okay, this is the thing. Okay, so these are some of the codes. You can I have kept all the codes in this NPTEL DLTA folder, in the DL codes folder. And DL codes, you can open this course from 36 to 47, all the codes for this convolution operation and convolution neural network, and you can just perform all your you can just run this course and see the results. Okay, that the code will give you. So this is the thing. Yeah, Supriya, any doubt?
Sir,
Yeah,
if the original image is also, if it is blurred,
yeah.
then can we extract the features from that?
Can you extract? Yeah, we can extract the feature from that.
So what kind of code we have to write for that thing?
If we have blurred and we want to
Yeah.
sharpen the image, so just put
Okay.
a convolution this just put a sharpen convolution filter, and you will extract this sharpened image, and after that you can perform your convolution operation, or just
So,
pass the image to this convolution neural network.
okay. Thank you, sir.
Yeah, okay. Now will be again now we will be going to the question answer session part. Okay, so again I am requesting everyone to first I'll be showing you the question. First you guess the solution, and then we will discuss the solution. So this is the first question. Consider an input image of size 1000 into 1000 into 10, where 10 refers to the number of channels. Suppose we want to apply a convolution operation on the entire image, sliding a kernel of size 1 into 1 into d. What should be the depth of the kernel? So any guesses for this?
10, maybe 10.
Yeah, 10, exactly 10, because here, as we do not know how many number of filters are there, so what we are for each layer we will apply the same convolution filter. So as we are applying the same convolution filter for each layer, so the depth of the entire convolution filter, if we just combine all the convolution filter of each layer, now the dimension or depth of the convolution filter will be equal to depth of the input image, that is 10. Okay, so 10 will be the answer. Okay, so in a convolution neural network, depth of the kernel must match the depth of the input image to ensure the dot product operation. Okay, just leave this. Given the input size was 1000 into 1000 into 10, 10 is the number of channel. The kernel must have same depth to process all the channels simultaneously. That means each layer you will just apply the same convolution for each layer one by one. So if I take the whole convolution as if I take each convolution as a whole convolution, so the depth of the convolution filter will be equal to depth of the input image, that is 10. Okay, so 10 will be the answer of this question. Okay, so is it clear to all of you? Now let's move to the next question. So this is the question for the same input image in question number 1. So what is the dimension of the image? 1000 into 1000 into 10. Okay, 1000 into 1000 into 10, that was your dimension. Okay, 1000 into 1000 into 10. Suppose that we apply the following kernels of different sizes. K1 is 3 cross 3, K2 is 7 cross 7, K3 17 cross 17, and K4 41 cross 41. Assume the stride equals to 1 and no zero padding. Among all this kernel, which one shrinks the output dimension the most? Okay, so option A is K1, option B K2, option C K3, and option B K4. So any guesses for this? This is the size of the filter. K1 size is 3 cross 3, K2 size is 7 cross 7, K3 17 cross 17, and K4 41 cross 41. Yeah, D. Yeah,
K4.
exactly D. So you have to just apply the formula. What was our formula? This was the formula that we have learned. Okay, this was the formula that we have learned. Yeah, this was the formula that we have learned. We have to apply this formula, W1 minus F plus 2P divided by S plus 1. Okay, this is the formula. So this is the formula we will apply for each of this kernel. Yeah, for each of this kernel we will apply the same formula. Yeah, here there is no padding, that is why P equals to 0. P equals to 0, so that is why P I have not written, and F is written in the form of K, so K equals to F here in the formula. So just put the formula I minus F plus 2P, P equals to 0, and this K equals to F, and S, the stride is given 1, then again there is no effect of the stride, and plus 1. So you will do this for the first kernel, that is 3 cross 3. For this 3 cross 3 kernel, the value of K will be 3, and your answer is coming 998. So this we are doing for either W1 or H1. W1 or H1. We are doing this. Let's say the input size was W into H into D. This was our input size, and this was our output size. Output size is W1. Output size is W1 into H1 into D. Now I am assuming the D is same, and I am just I have to look for W1 and H1. As W1 and H are same, W1 and H1 will also be same. So just by calculating one either W1 or H1, you will see how the size is shrinking. So let's say we are applying our formula for only width. So W1 will be equal to 1000 minus 3 divided by 1 plus 1 for this first filter. Similarly for second filter, 1000 minus 7 divided by 1 plus 1, that is the size is coming 994. For the third filter, size is coming 984. For the fourth filter, the size is coming 960. That means if I do the reduction of size, the shrinkage here is 40 for width. Similarly, shrinkage will be 40 for height. And D, let's say D is same, so that is why let's ignore D. So that is why this K4 filter has the maximum shrinkage for this W1 as well as this W1 as well as this H1. So the option D is the correct answer. Okay, so this is the thing. Is this clear to all of you? Okay. Now question number 3, which of the following statement about CNN are true? Option A, CNN is a feed forward network. Option B, weight sharing helps CNN to reduce the number of parameters. Option C, CNN is suitable for natural images. Option D, the shape of the input to the CNN network should be square. So any guesses for this?
A and C. A and B.
A and
A
B?
and B. A and B. A and B.
The shape of the input to the CNN network should be square.
No, no, A and B. B,
A,
B.
okay, A and B. Okay, CNN is suitable only for Nadia. Yeah, A and B are the correct answer. Okay, because you all know CNN is a feed forward network. Only we are applying two type of strategy in the feed forward network for making it from feed forward network to CNN. One is sparse connectivity and the other one is weight sharing. This two strategy we are applying to a feed forward network, and our feed forward network will be becoming the CNN. Okay, so these are the two things, these are the two strategy that we are applying this. So CNN is basically a feed forward network, so option A is correct. Second, weight sharing. Yeah, we are doing this two strategy. One is sparse connectivity, second is weight sharing. Why we are applying both this strategy? To reduce the number of parameter. So option B is also correct. Third, CNN is suitable only for natural image. No, natural image, we have different type of image. One is the black and white image, one is the RGB image, one can be also this X-ray image or any type of image. So for all type of image, our CNN can be applied, because only we need to learn the features. Okay, so for that, for any kind of images we can apply the CNN. So that is why this is false. D, the shape of the input to the CNN network should be square. There is no hard and fast rule for this, that shape should always be square. Even if the shape is rectangle, our CNN network will work fine. That is why this is also false. So option A as well as option B are the true options. Okay, so option A as well as option B are the correct answer. Okay, so is this question clear to all of you? Clear, right? So let's move on to the next question. Consider an input image of size 100 into 100 into 1. Suppose we use this kernel size 3 into 3 cross 3, 0 padding, p equals to 1, and stride value s equals to 3. What will be the output dimension? So very easy. Again you will apply the same formula, that is the output dimension will be equal to I plus 2p minus k or f, whatever you will say, divided by s plus 1. This is the formula that we have learnt again and again. Now we will apply the formula. See here, this is a square shape image, that means w1 is equal to h1. So just calculate either w is equal to h, so that is why either calculate w or either calculate h, and then just write the dimension. So let's say we are calculating w, so w will be equal to I plus 2p, w1 will be equal to I plus 2p minus f, okay, minus f divided by s and plus 1. This is the answer. So I, this is not 1, this is I. Okay, I is equal to 100. Okay, I is equal to 100, 2p, p equals to 1, that means plus 2, minus f, f is equal to 3, divided by s is equal to again 3, s is equal to 3 and plus 1. So that means 100 minus 100 plus 2 is 102, 102 minus 3 is 99, 99 by 3 is 33, 33 plus 1, that means our w1,
34.
yeah, w1 will be equal to 34. So our dimension will be equal to 34 cross 34 and cross 1, because our output or input depth is 1, that is why our output depth will also be 1. So this is the size of the output image. Okay, 34 cross 34 cross 1. Okay, so this is the thing. Yeah, so answer is this is an integer type question, that is why only 34 is written, but this is the output dimension 34 cross 34 cross 1. Okay, so this is the. So is it clear to all of you? Just you have to remember this formula. Okay, I plus 2p minus f divided by s plus 1. Okay. Yeah. Now let's move on to the next question. Again we have this question, but here they have asked how many number of parameters are there. Okay, not the output size but number of parameters. So consider an input image. This is the size of the input image, 100 cross 100 cross 3. Okay, suppose that we use a 10 kernel filters. Okay, each of size 1 cross 1. 0 padding, p equals to 1, stride value s equals to 2. Now again we will how many number of parameters are there. So they are asking how many number of parameter. So how we find the number of parameter? Number of parameter will be equal to your kernel size, that is f, into number of kernel filters. So let's say number of kernel filters is k or n. Okay, we'll just say number of kernel filters are k. So first what we need to do, first we need to first we need to calculate the uh, uh, this calculate this f, or the kernel size. Okay, so how we can calculate the kernel size? Kernel size is already given, that is 1 cross 1. Okay, so 1 cross 1 into number of filters, that is 3. Okay, into 3. 3 is the depth of the image. So our number of parameter, like, yeah, what are the parameter in the convolution neural network? Convolution neural network, the parameter are nothing but the kernel. Okay, the kernels are the parameter only, or the pixel of the kernel are the parameters only. So the pixel of kernel, we have been given only, we have 1 cross 1 size filter, and number of filters we are given, number of filters are 10. We have 10 number of filters. But another thing you have to keep in mind, these are 3D kernels. 3D kernels mean your depth will be equal to your depth of the input image. That is why 3 you have to multiply. So 1 cross 1 into 10 into depth also you have to multiply. So your answer will be coming 30. Okay, so the 30 is your number of parameters. So is it clear to all of you? Just you have to multiply the kernel size into this k, that is number of kernel filters. And also you have to keep in mind, this f does not only comprise the width and height, but this f also comprises the depth. That is why you have to multiply by depth. So your answer will be 1 cross 1 cross 3 into 10, that is 30. Okay, so this is the thing that you have to keep in mind. This is the formula of number of parameters. So is this thing clear to all of you? Clear, right? Okay, so which statement is true about the size of filters in the CNN? The size of filter does not affect the feature it captures. The size of filter only affects the computation time. C. Larger filters capture more global features. Option D. Smaller filters capture more local features. So any guesses for this? Okay, so let's start from one by one.
B.
Yeah, D. Okay, D. If D should be
No,
right.
no, B. B,
Okay,
B.
B. The size of filter only affects the computation time. Yeah, it affects the computation time, but only is written. That means it the option is saying it does not affect the feature it learns. So is it right? Because only is given, right? So that is why this thing is wrong. Because it will affect the computation time, but it will also affect the feature it captures, right? So that is why
Yeah.
option B is wrong. Option A, the size of filter does not affect the feature it captures. It affects the feature it captures. You have seen in the
Wrong.
convolution operation that how much big will be your feature filter, that will determine the size of the output image, or the the size of the output image or the output it captures. The output it captures is known as feature map, so it will affect the feature maps. Okay, so that is why option A is wrong. Option B, as only is there, it will affect the computation time, but as only written here, so that is why it is wrong. Larger feature will capture more global feature, true, because more will be the size of the filter, the more abstract representation it will capture, or more will be the size of the feature map. So that is why larger filter will capture more global features. Similarly, if the filters are small, it will capture more local features. So that is why option C as well as option D is your right answer. Okay, option C and option D is your correct answer. Option A cannot be correct. Okay, and option B is not correct because only is written. If only is not written, it affects the computation time, then it would be true, but as only is written in the option, that is why it is false. So option C as well as option D is your correct answer. Okay, so this is the thing. So let's move on to the next question. What is the motivation behind using multiple filters in one convolution layer? Option A, it reduce the complexity of the network. Option B, it reduce the size of the convolved image. Option C, insufficient information. Option D, each filter captures some feature of the image separately.
D, option D.
Yeah, option D, right? Option A, reduce complexity of the network. No, as we are applying more multiple filter, it will increase the complexity, because multiple filters mean more number of parameter. More number of parameters means it will increase the complexity of the network. So that is why this is false. It reduces the size of the convolved image. Yeah, it can reduce the size of the convolved image, but after each layer what we do is we apply some kind of pooling layer. Also in the last layer we are applying this fully connected layers, right? So that is why it will not reduce the size of the convolved image. Okay, the fully connected layer that we use for those purpose only, that means to restore the size again. So that is why option B is false. Option C, insufficient information, false. Option D is right. Each filter captures some feature of the image, and the output after applying each filter is known as feature map. Okay, so that is why option D is correct. Okay, so option D is the correct answer.
Sir, I have a doubt.
Yeah, please.
Sir, actually, we are applying multiple filters, but in the sequence of the filter we are applying affect the output. Suppose I'm having A, B, C, D filter.
Yeah.
So instead of I am applying first A filter, then B filter, then C filter, D filter. But if I apply D filter, then A filter, then B filter, and C filter, will it change the uh, output or the feature we capture?
Yeah, definitely it will change, right? Because each filter you will apply, like here you will apply 3 cross 3 filter, and after that you are applying 7 cross 7 filter. So this, in the first layer you will be convolution operation, you remember, right? This is the
Yeah.
convolution operation. So this is the convolution operation. Like here you are applying this filter, after that you are applying this filter. So this will be your output. Similarly, if size of the filter is different, also the pixel value is different, then the output will be different. So that is why the sequence, if you change the sequence, and your filter will have different size as well as different pixel values, so definitely your output will also change. Okay.
Okay.
Yeah. Okay, someone is joining, I think. Okay. Yeah. So which of the following architecture has the highest number of layers? Option A, alexnet. Option B, googlenet. Option C, resnet. And option D, vgg.
C,
That's
C.
not.
Yeah, resnet, right? Resnet 152s,
C.
152, yeah, 152 layers. Alexnet has how many layers? Alexnet has 16 layers, right? 16 or 8 layers? Alexnet has AlexNet has 8 layers, right? AlexNet and ZFnet has 8 layers, yeah. AlexNet and ZFnet has 8 layers. VGG 16 has 16 layers. VGG 19 has 19 layers. and googlenet has 22 layers and this resnet has 152 layer. Also there are several version of resnet. There was a version of resnet called resnet 50. Resnet 50 has 50 number of layer, but resnet will have maximum number of layer out of all this 4 option, right? Yeah, out of all this 4 option, resnet will have maximum number of layer for sure. Okay, so option C is the correct answer. Okay, resnet 152 152 layer. There is a version called resnet 50. It has 50 number of layers. So option C is the right answer. Okay. Yeah. Now let's move on to the next question. What is the purpose of guided propagation in CNN? To train the CNN to improve its accuracy on a given task, to reduce the size of the input image in order to speed up computation, to visualize which pixel of an image are most important for a particular class prediction. Option D, none of the above. Yeah, so this is question is again for the this pattern recognition thing only. So this code I have given the difference between the back propagation and guided back propagation. In back propagation, what we are doing whenever we are calculating gradient, we are conserving all the gradient. But in guided back propagation, whenever we are calculating gradient, wherever the gradient is coming negative, those gradient we are ignoring or we are equating to 0. The gradient which are coming positive only, those gradient we are taking. Okay, so this is the difference between back propagation and guided back propagation. Guided back propagation, we are only keeping the positive gradient. Okay, so why we do that? So we do that generally to visualize which pixel of an image are most important for a particular class prediction. Okay, so option C is the correct answer. So guided back propagation, it modifies the standard back propagation. Okay, so it is a back propagation only, but it modifies the guided back propagation by restricting negative gradient. Okay, so we are restricting negative gradient in case of guided back propagation, making visualization sharper and more interpretable. It highlights which part of the image contributes most to the CNN decision. Okay, so yeah, so how our decision is taking place? Our decision is taking place by learning this filters, right? So our decision is taking place by this algorithm known as back propagation. Okay, how you will learn this kernels? You will learn this kernels by back propagation only. Okay, so what is this guided back propagation doing is, if we are applying standard back propagation, and if we are visualizing which pixel of an image are most important, this standard back propagation, some of the gradient will be negative and some of the gradient will be positive. So the idea is the negative gradient will cancel the effect of the positive gradient. Okay, and in that part of the image, our image will be appearing black only. Okay, but here what we are interested to know the to learn the patterns, or see which pixel of an image are more important for a particular class prediction. So that is why in guided back propagation, what we do is we modify the standard back propagation, restricting the negative gradient. Okay, so option C is the correct answer. Okay, so this code I have provided, you can see the code and you can understand it. Okay, so this is the answer. Option C is the answer, to visualize which pixel of an image are more important for a particular class prediction. Okay, now let's move on to the next and the last question. Which of the following statement is true regarding the occlusion experiment in a CNN? It is a technique used to prevent overfitting in deep learning models. Option B, it is used to increase the number of filters in a convolution layer. Option C, it is used to determine importance of each feature map in the output of the network. Option D, it involves masking a portion of the input image which with a patch of zeros. Yeah, so Pradnya is telling option D. Yeah, option D is definitely right, because what we do in this occlusion experiment, we are masking the part of the image and we are seeing what is the drop in confidence. But the thing is, option C can also be correct. How it can be correct? See, the occlusion experiment, it is mainly used to assess which region of the input image are crucial for given prediction, right? However, it can be extended. There is an extended thing for this occlusion experiment to evaluate importance of individual feature map systematically by occluding or suppressing specific feature map at different layers in CNN and observing the effect of the final output. Okay, so what can be done in another version of a occlusion experiment? Each filter is learning some of the feature map, right? So if we can occlude some of the feature map and see in the output that either it can able to classify the final output or not. Like each layer we are just occluding that filter, occluding the abstract which it is learning in that layer. So what will happen is we can see that at the final output either we are able to still classify our output or not. So this is another you can say another version of this occlusion experiment. So that is why option C is also correct. And option D, you all know, it involves masking a portion of the input image with a patch of 0. Yeah, it is it involves the masking of a portion of image, and see that how much the drop in confidence is occurring during classification. So option D is always correct. Option C is another form of this occlusion experiment. Okay, so that is why option C is also correct. So C as well as D are the correct answer. Okay, so this is the thing. So is it clear to all of you? Clear, right? Okay, so by this I am ending the session for today. Please just look at the course, copy the course to your drive and just run the course. You will see exciting results, and also you can change the image, change the input image by any image that you provide, and you can see the results. Also what you can do is you can also change the network, like some cases I have used VGG16 or VGG19. You can change the network to alexnet or whatever resnet, any network you can choose, and then you can again see the results that are coming. So that thing you can do. Also another important tip is always as these are this involves so many computations, so that is why your CPU may not work well. So in the this Google Colab, you just go to this option called runtime and you select the runtime as GPU. Okay, from CPU just change the runtime to GPU. By doing that your code will run faster. Okay, so this is an important tip. And just copy the code to your drive and just run the code and just change some of the parameter. You can change some of the parameter and know the results. Okay, so these are the things.
Sir, I have doubt.
Yeah, please.
Sir, if I want to have that previous year assignment questions, where I will get it?
Previous year assignment question. I don't
Yes,
know.
sir.
I don't know exactly. Previous year. Why you want previous year assignment questions?
The exams are coming now. We have to see
Okay.
how to.
So exam, if you will do this assignment problem as well as the problem that is discussed by your TAs, so you will be pretty much on a good position to answer all the question in your examination. Okay.
Okay, so okay.
And all the previous year assignment question also would be based on the same logic, right? Same logic,
Uh,
only the data would be changed here and there, but logic would be same. So that
yeah, some
those
different questions. Some
those
different
question,
questions.
yeah, those question will be very much similar, so you
Okay,
won't get
okay.
much benefit. Okay, so that is why
Okay,
if
okay.
you will just do the assignment as well as these things that the TA are discussing, you will be in a good position to answer the question in your examination.
Okay, sir. Thank you.
Sir, actually the date is got over of filling the exam form. So can I give the exam still or
Actually,
next
I am
time?
just a TA of this course. So wherever you are getting those emails like this emails for this class announcement, etc., there you can just mail and ask them. Another thing what you can do, there is a Google group, right? In your this swam portal there is a Google group where you guys can ask question like any portion you are getting doubts, etc. So in that Google group you can just post your query that I just missed that examination filling date, so can you just open the portal again, like that, and they will answer you for sure. Okay.
Okay, sir.
So by this I am ending the session for today. We have two more weeks, like week 11 and week 12. Also, what I will do, I will take a revision week at the last. So what I am planning is I will be taking the class on Friday this week. Week 11 I will take the class on Friday. Week 12 will be on Tuesday as it is, and the extra session I will be taking on next Friday. So your my session will be on this Friday, next Tuesday, as well as next Friday. Okay, 2 weeks and one I will take an extra session to sum up. Okay.
Thanks.
Okay. So bye everyone.
Thank you.
We will meet
Sir, will we be able to hear that recording immediately after this session?
this session.
Recording.
This session.
Yeah.
Yeah,
Yeah. Week 10.
immediately, not immediately, but within one
Okay.
hour you can see. In that,
Okay. Okay.
yeah, within 1 hour, I will try to upload as soon as possible. But in
Okay.
1 hour or at night, you can see the recording. Okay.
It's really useful, sir. Very much. That's why.
Okay.
Thank you.